So now that we understand each other, lecture 3.4 is the sort of the second part of this bridge between a linear graph and a state space model. So this is the algorithm. At long last, we consider an algorithm to generate a state space model from a linear graph model. In the following, we will consider a connected graph. Connected meaning that you can go from any one node to any other node on the graph by following its branches. With B branches, of which S are sources, just like before, split between through variable sources and across variable sources. There are two B minus S unknown across and through variables, just like before when we were discussing it. So that's how many equations we need. We have B minus S elemental equations, and for the rest we will write continuity and compatibility equations. N is the number of nodes. So here we go. Here is so the book has its own procedure list. Mine's a little different. They're equivalent, so you can, if you like the version in the book, that's fine, you can use that version. I think that this version is a little bit easier. It's like more minimal, and it doesn't have as much explanation in it. And so I think it's a little bit easier to follow through as a procedure. So this is split into two, so one A through G, and then two A through something. And step one is essentially writing all the equations down. Step two is eliminating variables and putting it into a standard form. Okay, so actually step one, I think, is in a lot of ways the easier of the two from an actual standpoint of writing things down. Although this is the part where if you mess up, it's a big deal because there's no chance of getting it right if you mess up on the first part. The second part is essentially just algebra, okay? And most people tend to get one down pat, okay? Even though like that's where all the concepts are, and that's where like you have to choose the correct equations to write down. Most people will get that without too much trouble. Step two is where people get bogged down in the algebra. So I'll discuss a little bit more some ways to try to mitigate that getting bogged down. But step one, I think is actually the really important part, because you can take the result of step one and hand it to several different resources, computer-based resources that I'll give you to do step two for you. So never fear. We can have computers do these things. Okay, so step one is to derive 2b minus s, so the number 2 times the number of passive elements in the linear graph, independent differential and algebraic equations from elemental, continuity, and compatibility equations. So essentially write elemental equations, continuity equations, and compatibility equations. This procedure is going to help us to just write down the correct ones that are going to help us get to the end effectively and not lose our way. So the first step is to draw a normal tree. So last lecture we learned how to do that. Bang. B, identify primary and secondary variables. So just like we did, we said, oh, okay, primary are across on branches and through on links. Secondary are through on branches, across on links. Done. So we just write a list of them. C, select the state variables to be across variables on A-type branches and through variables on T-type links. Okay? So that's the selection of state variables, which is nice. Actually, it helps us to find our state variables very quickly. And once we know our state variables, what do we know about the system? A sort of key aspect of the system, we know. The system order, right? We know the order of the system, we defined it to be the number of state variables, right? So once we find the state variables, we know what the order of the system is. And notice that A-types in the normal tree, that is A-type branches, are independent energy storage elements. And T-type links, so T-types not in the normal tree, are independent energy storage elements. So pretty much we get a state variable from each independent energy storage element. Okay? D, define the state vector x. So take your state variables from the previous step, put them in a vector. Your input vector, which is to identify the inputs in the system, put them in a vector. And then the output vector, which is identify what your outputs are going to be and put them in a vector. Okay? E, write an elemental equation for each passive element. So each passive element has an elemental equation. We write it down. F, write a continuity equation for each passive branch by drawing a contour intersecting that and no other branch. Solve each for the secondary through variable associated with that branch. So it's a little bit lengthy in the description, but essentially we're going to find each passive element in the normal tree. So if I go back over here, each passive element in the normal tree, so C is a passive element in the normal tree, R2 is a passive element in the normal tree. And I want to write a contour that goes through one and only one element in the normal tree. So, like, I don't want to do this because we're going to do this as an example in a moment, so I don't want to go through this. But essentially, we need to cut this one once and cut this one once with the contour. All right, so we'll come back to that. G is to write a compatibility equation for each passive link by temporarily including it in the tree and finding the compatibility equation for the resulting loop. And then solve each of the compatibility equations for the secondary across variable associated with that branch. So pretty much what we're doing is we're going to say, oh, let's pretend like R1 is actually in this tree for just a moment. We know by definition, or by construction, I guess, that it's going to create a loop when we put it in, right? So we just write the compatibility equation for that loop. It's just like KVL for that loop, right? And we need to solve for the voltage, the across variable for the element that we placed into the tree. Okay. And that is all we need to do for part one. And what I'm telling you is that this is something that I think very doable. You guys can all do this. And what's cool is you can get to this point, and really what's left is algebra. So you write these things very systematically, you go through the steps, and then the rest is just algebra, which for the problems that you're going to have to do by hand in class, and on like an exam in class, I'm not going to give you guys ones that are going to have a lot of algebra to do, right? I'm going to make it so that the algebra is easy on those. If it's going to be something that's more complex, we'll talk about some other strategies. So now, before we go on to 2, do these remind you of anything, these steps? It's like a lot like our 1 through 5 steps from our circuit analysis technique, right? Except that we didn't just sort of like tell you to find some KVL and KCL equations and not give you any guidance. We give you very specific guidance on which ones to write, right? Which continuity equations, which compatibility equations. And it will always be the correct ones that you need, and it won't be any extras that you don't need. Unlike when we did KCL and KVL before, it was just like, well, hopefully you don't end up with too many or too few. Do you have all the ones you needed? We'll have exactly the right number. We'll be ready to do the solution. And they'll actually be solved for the variables we can eliminate immediately, which is great. Okay, so step 2. Eliminate variables that are not state or input variables and their derivatives. The following procedure is recommended. So the first one, A, is highly recommended. Eliminate all secondary variables by substitution into the elemental equations of the continuity and compatibility equations. We solved all of the continuity and compatibility equations for the secondary variable, the only secondary variable by construction that shows up in each of them, okay? We can use that to eliminate the secondary variable from every elemental equation. And that's what we can do as our first. So 2A is to eliminate all the secondary variables. So we had several unknowns, and we pretty much dropped that by a factor of 2 with this, right? Which is nice. Drop it by a factor of 2. We eliminated half of them, and half of the number of equations. So now we're just left with the elemental equations with the secondary variables eliminated. So just primary variables remaining and inputs. Okay. Good. Then we reduce the resulting set of equations to n in state and input variables only. So we can, when we have a system of order n, which is usually the symbol we use for the system order, which is the number of state variables, right? We have a system with n state variables, system order is n. We can eliminate variables down to the point where we have just state variables and input variables in the equations, and there will be n equations left, okay? And they're going to all be first order differential equations when we get there. That's what they'll all be. Now, try using elimination first. If it's a small system, like you're doing it on your homework or you're doing in class on an exam, try just using pretty straightforward algebraic technique, substitution, to eliminate stuff, okay? The variables that you don't want. If that doesn't work, there is a linear algebra technique that works every time, but you guys haven't had linear algebra, at least not all of you have had it. So I don't expect you to be able to do that, and I won't teach it in class. It is in the book, though, if you want to know. But it's a general method that works for every linear system. And I also wrote a Mathematica library that you can use to do this in the next few steps as well. So it's called State. It's a package, I guess, Mathematica package they call it. And you can, so I'll send it to you guys. So on the computers downstairs we have Mathematica. Pretty much what you can do is you can give it the equations that you derive from up here, and it will do step 2 for you in its full glory, including the algebra part here. We have to eliminate variables. It'll do all of that. And it'll write it into standard form. A former student from here who graduated, he's now a PhD student up at UW. He is in the final stages of writing this website version of that package, essentially, so that you guys don't even have to have Mathematica. You can just go to this website, and then you can put in your equations, and it'll do the algebra for you. pretty nice. And it gives it to you in different languages. You can get output, so LaTeX for typing up the equations, or in Python, or in MATLAB, or in Mathematica. I think that might be output. So anyways, it's pretty cool. So I'll send out those resources for you. But when you're doing it by hand, which is something you guys will need to be able to do, right? Because you're going to have an in-class exam, you're going to have to do it by hand, right? So got to do it. Write the result in standard form. So standard forms, equations 3.1a and 3.2a, are the state equations. So the first one is just the general nonlinear one. I'm going to use the dot notation here. X dot equals f of x u t, right? So that's the nonlinear version. The linear version is x dot equals ax plus bu. So state equations. So the state equations are the result then of all this work up to step C. So 1, A through G or whatever it was, G, and then 2, A through C are all to construct the state equations. Pretty much. And we do a little bit of work to construct the output too. We laid the groundwork for it. And then these last two steps are to form the output equation. So these are just two different forms. Really, I shouldn't say that there are multiple equations. This is just two different forms of the same state equation, right? The output equation is found from the next two. So express the output variables in terms of state and input variables using any of the elemental continuity or compatibility equations as needed. So if we have outputs, maybe those outputs are state variables, in which case you're done because they're already in terms of state variables. But maybe they're not state variables. Maybe you have some voltage across a resistor that's not a state variable. You need to be able to write that using your equations that you know, the relationships that you know, in terms of state and input variables. So once you do that, the next step is to write the result in standard form. So equation 3.1b for the general nonlinear form, or for the linear form, 3.2b gives that. So we have y equals g, so this is 3.1b, g of x u t. These are vector valued functions. They should have vector arrows over them. And then y is equal to, the linear version is cx plus du, right? So the output. Equation. And that is the whole process, okay? So we're going to start an example today. We're going to do step 1, so 1A through G of an example. So we're going to use the same linear graph that we used as our inline example for the normal tree. So for the electronic system shown, find a state space model with outputs IL, IS, and VR2. Okay, so 3 outputs. Our first step is to actually, so I can number it for you guys if you guys want. We'll do 2A. No, 1A. I don't know why I would start with 2. 1A. Boom. So 1A is draw a normal tree. Okay, so we already did that, right?
Mm-hmm.
So let's just remember what we did. We drew the nodes. We have to include all the nodes. And then we included the cross variable source. Then we included the A types. And then we included the D types. We could only include this D type because that one would create a loop. And we couldn't include any T types because it would have created a loop. So there was our tree. So normal tree. Now I go back to black here. Okay, so 1B. What was that? Identify primary and secondary variables. So let's just list primary. So we'll do first primary variables are cross variables on branches. So VS, VC, VR2, and then through variables through links. So IR1, and then what's the last one? IL. Very good. Our secondary variables, you can go through and go back to the definition, but it's just the opposite, right? So I just permute the list above. So I say, oh, well, this is IS, IC, IR2, VR1, VL. Secondary variables. Cool. 1C. Select the state variables to be across variables on A-type branches and through variables on T-type links. So we have one A-type branch and one T-type link. So the state variables are VC, across variables on A-type branches, and the current through the inductor, so the through variable for T-type links. Notice how we're like building on these definitions, like through variables, links, branches. We're slowly making our way up. Okay, 1D. Define the state vector x, input vector u, and output vector y. So the state vector is just a listing of the state variables, right? So VC, IL. Could we have chosen IL, VC? Yeah, no reason we couldn't have, but once you choose something, you should stick to it. So shows that. Then let's do input. So U is equal to, how many inputs do we have? One. So it's a 1 by 1, right? And what is the value? Or what? VS. One input, VS. And outputs are prescribed. They have to be given in the problem, or you have to know as a designer like what you care about, right? So we care about, apparently, the current through the inductor, the current being delivered by the source, and VR2, the voltage across resistor 2. So we can just list those. So IL, IS, and VR2. Any questions on that? All right, we are ready for E. E says to write an elemental equation for each passive element. Well, we have 4 passive elements, right? The 2 resistors, the capacitor, and the inductor. So I like to use this sort of table form where I draw the symbol representing each of the elements. So elemental. So I'm going to do C, L, R1, R2. So the first elemental equation is the elemental equation for a capacitor, which is dV C dt equals 1 over C IC, right? Should look familiar, I hope. And then the elemental equation for an inductor is DIL dt equals 1 over L I L. What is the elemental equation for resistor 1? Yeah? Good. So there are our elemental equations. Great. Now we need some continuity and compatibility equations. So 1, F. The first one is continuity. You can do it in either order of continuity, but for some reason I started doing continuity first and I'm just stuck in my ways. So continuity equation. What we need to do is we need to write these contours, right? Draw these contours. We need a contour to cut each of these passive branches in the normal tree and no other branches. So the first one's pretty easy. We can cut one branch in the normal tree, one passive branch in the normal tree, and only one, and that is R2 with this contour, right? So that's a nice one. And what we're going to do is we're going to jump immediately to this second part of this 1F, which is to solve for the secondary variable associated with that branch that you cut, okay? Which is IR2, right? The continuity equation always deals with through variables, right? So it's IR2. You want to solve for IR2. So remember when I was teaching you guys how to do these, I said, oh, I like to just sort of take the shortcut where I solve the equation for the variable that I want from the very beginning. And so I'm going to start doing that every time now so that you guys can kind of see me go through those steps, and hopefully it'll help you do that too, because it does save some time. So when you are considering this branch, you want to know what IR2 equals. So IR2 is going in, so it must equal everything going out, right? So it's going into the contour, it must equal everything going out of the contour. So IR2 has to equal IL in this case. So IR2 equals IL. And we need another one that cuts this branch, right? But we can't use this. Why can't we?
It cuts 2 branches.
Cuts 2 branches, and we can't cut 2 branches. We only cut 1 branch. So we have 2 options. We can either do this one, only cuts the 1, or we can do this one. And let's use this one because I kind of like it better. And it's prettier when I drew it. And it's still up there. All good reasons. But any of them would be fine. So in this case, we want to write the equation for the branch that we cut, right? So IC is what we want the equation for. And IC is leaving the contour. So we know that IC must be equal to everything going into the contour, right? So IC must be equal to IR1, which is going in, minus IL, which is going out. Okay, so IC equals IR1 minus IL. If you got confused on that, totally fine. You could have just said, oh, it's a node. I'm going to just write the sum of everything going in and subtract everything going out equals 0. You can do that too. You just have to then solve for IC, which is like one extra step, but no big deal either way. So now we have our last step of the one part. So G, 1G, compatibility. So compatibility, the equations for compatibility are found by including each of these links in the normal tree momentarily, sort of like pretending like they're in there, and then writing the compatibility equation for that loop. It's as simple as that, and then you just need to solve for VR1, the across variable associated with the link that you included, and VL, the across variable associated with the other link that you included in the other equation. But once again, I like to skip right to the solution because it's a little bit faster. We don't have to write it twice. And it also just helps me remember what I'm supposed to be solving for. I'm always supposed to be solving for the variable associated with the element that we're either cutting in this continuity equation version or including in the normal tree in this compatibility equation. So, and we'll do the R1 loop first. So if we include R1, we create this loop here, right? So we could just start anywhere, go around the loop, add them up, equals 0, and solve for VR1. Or we could think of it like a vector, where VR1 goes from this node to this node. So it must equal the vector that goes from this node to the same node, if following the direction of the arrows, right? So VR1 must be equal to VS in the same direction, minus VC, because it's pointed against me. So VS in the direction of VS, minus VC, because it's pointed against me there. So VR1 equals VS minus VC. Similarly, we could include the inductor element, and that would create this loop here, right? And we could go start any node, go around the loop, sum up the drops, subtract the gains, equals 0, solve for VL. Or we could say the vector goes from this node to this node is VL. It has to be equal to negative VR2, because I'm going against it, negative VR2 plus VC. So VL equals negative VR2 plus VC. So the technique is to include it, find the loop, start at the tail, sum the drops, so this is a gain, so you got to subtract, sum, until you reach the head of the branch that you're including, of the link that you're including. Okay, so that is it. So we got all the way through 1, right? So now we got to do, we have our equations, and we could be off to the races, right, with our finding the state equation and the output equation. But there's a little bit of algebra that remains. But we're pretty much there. We set the stage. In a certain sense, we did the hard part. Now is just the tedious part as well. All right.
I got a question.
Yeah, what's up?
The inductor elements equation, I thought it was VL instead of IL.
Oh, yeah, right here?
Yeah.
Good
That's
call.
what I thought. I was like, dang, I guess I got it
I don't
wrong.
want to mess the lecture.
No, I'm glad. I'm glad you said something.
I wrote VL.
So DIL, DT.
IL.
is not equal to 1 over IL. It's equal to 1 over LVL.
So I always remember it as like the opposites of counter and inductor like the equation.
Yeah, exactly. I just,
No, I remembered it like that too.
it was,
I was like, what's going on?
we'll call it an error. That's what it was.
I was like, oh,
The whole structure.